In this video, we will summarize the expected learning outcomes of Chapter 5, Radioactivity in the form of concept map. In this chapter, we will learn and understand more about radioactivity. There are 5 main sections in this chapter. 5.1 Nucleus of an atom. 5.2 Radioactive decay. 5.3 Radioisotopes. 5.4 Nuclear energy. 5.5 Importance of proper management of radioactive substances. In section 5.1, we will learn about the nucleus of an atom. At the end of this section, you should be able to describe the composition of the nucleus of an atom in terms of protons and neutrons, define proton number Z and nucleon number A, explain the term nuclide and use the nuclide notation, define the term isotope. In section 5.2, we will learn about radioactive decay. At the end of this section, you should be able to state what radioactivity is, name common detectors for radioactive emissions, compare the 3 kinds of radioactive emissions in terms of their nature, explain what radioactive decay is, use equations to represent changes in the composition of the nucleus when particles are emitted. Explain half-life, determine half-life from a decay curve, solve problems involving half-life. In section 5.3, we will learn about the uses of radioisotopes. At the end of this section, you should be able to define radioisotopes, name examples of radioisotopes, describe applications of radioisotopes. In section 5.4, we will learn about nuclear energy. At the end of this section, you should be able to define atomic mass unit, AMU, describe nuclear fission, give examples of nuclear fission, describe chain reactions, describe nuclear fusion, give examples of nuclear fusion, relate the release of energy in a nuclear reaction with the change of mass, according to the equation E equal to mc square. Describe the generation of electricity from nuclear fission, justify the use of nuclear fission in the generation of electricity, solve problems involving nuclear energy. At the end of this chapter, section 5.5, we will learn about the importance of proper management of radioactive substances. At the end of this section, you should be able to describe the negative effects of radioactive substances. Describe safety precautions needed in the handling of radioactive substances. Describe the management of radioactive waste.
By the end of this video, you should be able to describe early ideas of the structure of atoms. You should then be able to describe the alpha scattering experiment, which was used to work out the nuclear model of atomic structure. And finally, you should be able to describe the discovery of electron energy levels, the proton and the neutron. Now, thousands of years ago, the ancient Greeks believed that everything's made of atoms. They thought that atoms are tiny spheres that can't be divided. That idea was accepted for hundreds of years. However, in 1897, scientists discovered that atoms contain tiny negative particles. They called these electrons. Now, this was a really big discovery because it showed that atoms are not tiny spheres that cannot be divided. Atoms must have an internal structure. So scientists now suggested a different model for the structure of atoms, and they called this the plum pudding model. The plum pudding model suggested that an atom is a ball of positive charge with negative electrons embedded in it. So I'm showing you the plum pudding model here. You can see that we've got a ball of positive charge, and embedded in it, we've got negative electrons. Now, scientists wanted to know if the plum pudding model was correct, and to find this out, they carried out an experiment. We call this the alpha scattering experiment, and you need to be able to describe it. First, the scientists took a piece of gold foil, just like this one here. The reason that they used gold is that we can hammer gold out into very thin foil, just a few atoms thick. They then fired tiny particles at the gold foil. We call these alpha particles, and you'll find out more about these in later videos. Alpha particles have a positive charge. The first thing they saw was that most of the alpha particles passed straight through the gold foil without changing direction. Sometimes an alpha particle was deflected. In other words, it changed direction as it passed through the gold foil, like this. And sometimes an alpha particle simply bounced straight back off the gold foil. So let's look at what scientists worked out from these results. The fact that most of the alpha particles went straight through the gold foil told the scientists that atoms are mainly empty space. This meant that the plum pudding model had to be wrong. Secondly, because some of the alpha particles were deflected, this told the scientists that the center of the atom must have a positive charge, and that repelled the alpha particles. And finally, because some alpha particles bounced straight back, this told the scientists that the mass of the atom must be concentrated in the center. We now call the central part of an atom the nucleus. When an alpha particle collides directly with the nucleus, it simply bounces back in the original direction. So from these results, scientists replaced the plum pudding model with the nuclear model, and I'm showing you that here. So most of the atom simply empty space. In the center, we've got a tiny positive nucleus containing almost all of the mass, and around the edge, we've got negative electrons. Now, the scientist Niels Bohr proposed that electrons orbit the nucleus at specific distances rather than just in a general area. Bohr's proposal was accepted because it agreed with the results of experiments by other scientists. We now call these orbits energy levels or shells. So here's the updated nuclear model with the electrons in energy levels. Several years later, scientists found that the positive charge in the nucleus is due to positive particles, which they called protons. And around 20 years after the nuclear model was first proposed, the scientist James Chadwick discovered that the nucleus also contains neutrons, and neutrons have got no charge, they're neutral. Remember, you'll find plenty of questions on this topic in my Vision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to describe early ideas of the structure of atoms. You should then be able to describe the alpha scattering experiment, which was used to work out the nuclear model of atomic structure. And finally, you should be able to describe the discovery of electron energy levels, the proton and the neutron. By the end of this video, you should be able to describe what's meant by radioactive decay. You should then be able to describe the 4 types of nuclear radiation. I should point out that some of this material can seem a bit complicated initially, but it's not as tricky as it looks, so bear with it. Recently, we looked at the idea of isotopes. We saw that isotopes are atoms of the same element with different numbers of neutrons. I'm showing you 3 isotopes of carbon here. Now, carbon-14 is actually a radioactive isotope, so let's look at what that means. The first key idea to get is that some isotopes have got an unstable nucleus. To become stable, the nucleus gives out radiation, and scientists call this process radioactive decay. I'm showing you a radioactive atom here. As you can see, the atom's giving out radiation from the nucleus, so it's undergoing radioactive decay. Now, a really important point about radioactive decay is that it's a completely random process. Scientists cannot predict when a nucleus will decay. Now, the activity is the rate at which a source of unstable nuclei decay. Activity is measured in becquerel, and that has the symbol capital B, lowercase q. 1 becquerel equals 1 decay per second. To measure the activity of a radioactive source, we can use a Geiger-Müller tube such as this one, and you may have seen one of these in school. The count rate is the number of decays recorded each second by a detector such as a Geiger-Müller tube. Now, I should point out that count rate is not the same as activity. That's due to background radiation, which we look at in a later video. Okay, so we know that radioactive nuclei give out radiation. So let's take a closer look now at what this means. There are 4 different types of radiation which can be given out by an unstable nucleus. The first kind of radiation is called an alpha particle. We saw this before when we looked at the alpha scattering experiment. Alpha particles consist of 2 protons and 2 neutrons. That means that an alpha particle is the same as the nucleus of a helium atom. You don't need to get too bogged down by that idea, but you do need to remember it for your exam. The second type of radiation is called a beta particle. A beta particle is simply an electron which is ejected from the nucleus at very high speed. Now we've already seen that the nucleus of atoms does not contain electrons, so where does the beta particle come from? Well, the answer is that the beta particle is formed inside the nucleus when a neutron changes into a proton and an electron. The electron is ejected from the nucleus, and we now call it a beta particle. Okay, the third type of radiation is called a gamma ray. Gamma rays are not particles. They're a type of electromagnetic radiation from the nucleus. Finally, the fourth type of radiation that's sometimes given out by unstable nucleus is a neutron. Remember, you'll find plenty of questions on radioactivity and radiation in my revision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to describe what's meant by radioactive decay. You should then be able to describe the four types of nuclear radiation. By the end of this video, you should be able to describe the properties of alpha, beta, and gamma radiation. These include their range in air, their penetrating power, and their ionizing power. In the last video, we saw that some isotopes are radioactive, and that means that their nuclei decay and they release radiation. That's a random process, so we cannot predict when it will happen. Three types of radiation are alpha particles, beta particles, and gamma radiation. In this video, we're going to look at the properties of these, so let's get started. The first key property is their range in air. Alpha particles are large. That means that they can travel around 5 centimeters in air before they collide with air particles and stop. Beta particles, on the other hand, can travel further. They can reach around 15 centimeters in air before stopping. Now, gamma radiation can travel much further than either alpha or beta particles, so gamma radiation travels several meters in air before stopping. Okay, the next key property is penetrating power, and this tells us what type of material is required to stop each form of radiation. So starting with alpha particles, these are relatively easy to stop. In fact, alpha particles are stopped by a single sheet of paper. Beta particles are harder to stop. In order to stop beta particles, we need a few millimeters of aluminium. Gamma radiation is even harder to stop, so gamma radiation is stopped by several centimeters of lead. Okay, the final property we need to look at is ionizing power. So first of all, we need to explore what that means. When radiation collides with atoms, that can cause the atoms to lose electrons and form ions. And we saw in an earlier video that ions are atoms with a charge. Now, each type of radiation has a different ionizing power. Alpha particles are very strongly ionizing. That means they can produce a lot of ions when they collide with the material. Beta particles are quite strongly ionizing, but not as ionizing as alpha particles. And finally, gamma radiation is only weakly ionizing. Remember, you'll find plenty of questions on the properties of radiation in my revision workbook, and you can get that by clicking on the link above. Okay, so hopefully now you should be able to describe the properties of alpha, beta, and gamma radiation.